Okay, let's continue our survey of Banach algebras. And to begin with, let's look at some simple algebraic properties of the spectrum. That is, properties which make sense for any algebra not necessarily equipped with a norm. First of all, let's look how the spectrum behaves under homomorphisms. We have the following proposition. Well, actually, this is not a theorem, it's rather a simple observation. If we have two unital algebras, A and B, and a unital algebra homomorphism, that is, a homomorphism which takes the identity of A to the identity of B, then, first of all, it takes invertibles of A to invertibles of B, which is more or less immediate. And by the definition of the spectrum, this readily implies that we have the following inclusion. Phi reduces the spectrum in this sense. So this inclusion holds for any element in A. This is immediate from the definition because, well, if lambda is not in the spectrum of phi of A, then A minus lambda is invertible, so phi of A minus lambda is also invertible. And so the complement of this set is contained in the complement of this set. And for the same reason, phi takes non-invertibles of A to non-invertibles of B, if and only if phi preserves the spectrum. If the spectrum of phi of A equals the spectrum of A for every element in A. This is also immediate from the definition of the spectrum. And in this case, we usually say that phi is spectrum preserving. Let's look at a classical example of a spectrum preserving homomorphism. This example is usually considered in standard courses of functional analysis. If we take a measure space, a sigma finite measure space, and consider a map phi from L infinity of x, from the algebra of essentially bounded measurable functions, to the algebra of bounded linear operators on L2, on the Hilbert space L2 of x mu. And this homomorphism takes every function f to the multiplication operator mf. So mf acts as a pointwise multiplication by f. Then it's a standard fact then that the spectrum of this operator, mf, is exactly the essential range of f, which was defined at the previous lecture. And we remember that this is nothing but the spectrum of little f considered as an element of L infinity. So we see that phi is spectrum preserving. A simple corollary of this observation is that if we have a unital algebra A, and suppose that B is a unital subalgebra, that is a subalgebra of A, such that the identity of A is contained in B. So they have a common identity. And in this case, for every element little b of B, we'll have the following inclusion. The spectrum of B calculated with respect to the bigger algebra A is contained in the spectrum calculated with respect to the smaller algebra B. This is just a special case of this inclusion. We just apply it to the inclusion map of B into A. There are many concrete important cases where this inclusion is actually an equality. And there is a special terminology for this situation. We say that B is spectrally invariant. Spectrally invariant in A. If these two spectra are the same, if for every little b in B, the following equality holds. And by looking at part 3 of this observation, we see that this happens if and only if non-invertibles of B are contained in the non-invertibles of A. Or equivalently, this means that if an element sits in B and is invertible in A, then it is also invertible in B. So we have this equality. And here are some examples of subalgebras which are and which are not spectrally invariant. First of all, if we take a topological space X, then it's clear that the algebra of continuous functions on X is spectrally invariant in the algebra of all functions on X. This is true for any topological space, for the simple reason that if F is continuous and is nowhere 0, then 1 over F is also continuous. Another example, if we take a Banach space E, then the algebra of bounded linear operators on E is spectrally invariant in the algebra of all linear operators on E. And this is true for any Banach space. This is not trivial from, this is not immediate from the definition, but this is just an equivalent form of Banach's inverse mapping theorem, which states that if a bounded linear operator on a Banach space is bijective, then the inverse operator is also bounded. And probably the simplest known example is the algebra of bounded functions, little L infinity of X, where X is a set. So if X is an infinite set, then this subalgebra is not spectrally invariant. Is not spectrally invariant for any infinite set X. Well, indeed, for any infinite set, it's rather easy to construct a bounded function which is nowhere vanishing, but which is not bounded away from 0. So it will be invertible here, but not here. And so this algebra is not spectrally invariant. Another useful algebraic property of the spectrum is the so-called spectral mapping theorem, or more exactly the polynomial spectral mapping theorem. If A is a unital algebra, little a is an element in our algebra, and F is a polynomial in one variable, then we can substitute A to F. So the element f of A is well defined. So what can we say about the spectrum of this element? Well, the spectrum of this element is given by the following simple and easy to remember formula. And this formula is true almost always, except for the only exceptional case where the spectrum is empty, unless the spectrum is empty and F is a constant. Well, because if the spectrum is empty, then the right-hand side is also empty, but the left-hand side, if F is a constant, then f of A is also a constant in our algebra, and its spectrum is non-empty. But this is the only exception. In all other cases, this formula is true. And in fact, this formula has many functional analytic counterparts. Maybe at the next lecture, we'll discuss a continuous version for this formula in the context of C-star algebras. A related result is about the spectrum of the inverse element. For every invertible element little a of A, the spectrum of the inverse element consists of all numbers of the form lambda inverse, where lambda runs over the spectrum of A. Let's now come back to Banach algebras. And let's discuss, let's recall the notion of a spectral radius in Banach algebras. So suppose that A is a Banach algebra, and little a is an element of A. Now, we define the spectral radius of this element, little a, as follows. This is a number defined to be the supremum of the modulus of lambda, where lambda runs over the spectrum. If A is not assumed to be unital, then of course we have to consider the non-unital spectrum here. But on the other hand, let me remark that if A is unital, then we can consider the usual spectrum, and the definition will be the same. Well, indeed, let's recall that if A is unital, then the only possible difference between sigma and sigma prime is 0. So 0 is always in the non-unital spectrum, but is not always in the spectrum. But clearly this doesn't affect the supremum. So these, if A is unital, then these two numbers are the same. Let's observe that, first of all, that this number is well defined, because the spectrum is non-empty, as was discussed in the previous lecture. It is non-empty, and moreover, it is finite. This number is finite because the spectrum is compact. So the spectral radius is a positive number, a non-negative number. Sorry, a non-negative number. Sometimes it is 0. Let me also remark that let's recall that for every lambda in the spectrum, we have the following inequality. Lambda is less than or equal to the norm. This is one of the statements of Gelfand's theorem. And this implies that the spectral radius, if we take the supremum over lambda, we see that the spectral radius is less than or equal to the norm. Sometimes these two numbers are the same. For example, if we take the algebra little L infinity of x, the algebra of bounded functions on any set x, then for every function, for every bounded function f, its spectral radius is equal to the norm. Well, indeed, the spectral radius is the spectrum is the closure of the range of f. So the spectral radius is the supremum of the absolute values of numbers in the range, but this is nothing but the supremum norm. So these numbers are the same. Another classical example from finite dimensional linear algebra is the case where the case of a self-adjoint linear operator on a finite dimensional Hilbert or Hermitian space. If A is B of H, where H is a finite dimensional Hilbert space, And suppose that little a, is an operator which is written by a diagonal matrix with respect to a suitable orthonormal basis. It's well known that if A is self-adjoint, then we can always find such a basis that the respective matrix will be diagonal. Then, again, we have the same equality. The spectral radius of A is equal to the norm. Well, indeed, the spectrum is precisely the set of eigenvalues which are on the diagonal. So the spectral radius is the maximum of these numbers. And clearly, this is nothing but the norm, nothing but the operator norm. So in this case, again, we have an equality between the spectral radius and the norm. Probably the simplest non-example, that is an example of a situation where this inequality is strict. Again, let's consider the algebra of operators now on the two-dimensional space C2, and let's consider an operator given by the following matrix. Then the spectrum of this operator is 0, because the matrix is upper triangular, and the numbers, both numbers on the diagonal are 0. So the spectral radius is 0, but of course the norm is not 0, because the operator is non-zero. So in this case, the spectral radius is less than the norm. And the reason for this example is that A is nilpotent. Actually, it's a simple exercise to show that, which holds in any unital algebra, if little a is a nilpotent element, then the spectrum is 0. And this is true for any algebra. So for nilpotent elements of Banach algebra, for non-zero nilpotent elements, the spectral radius is always smaller than the norm. And in the general case, the spectral radius is given by a useful formula. The respective result is sometimes called the Berling-Gelfand formula. If A is a Banach algebra and little a is an element in A, then the spectral radius of A is equal to the following limit at infinity of the following sequence. So for every n, we take the nth power of A, take the norm, and then take the nth root of this number, and the limit of the sequence exists and is equal to the spectral radius. Or equivalently, we can replace the limit by the infimum over all positive integers, and the result will be the same. This formula is quite useful.
Shouldn't we write lim, like lower lim?
No, we can of course write lim inf or lim sup, but actually the limit exists. This is a part of the theorem. This is part of the theorem that the limit exists. Actually, this result is due to Gelfand. And the Berling proved this result earlier, but not for all Banach algebras, but for a very concrete specific case of weighted L1 convolution algebras on the integers. Such algebras are now called Berling algebras. But his proof worked only for this concrete case. And the general case is due to Gelfand. Roughly the idea of the proof is as follows. This inequality is more or less easy. It follows from the spectrum mapping formula. We simply apply this inequality to lambda to the power n. Lambda to the power n sits in the spectrum of A to the power n, and so then take the nth root and take the infimum, and so this number is less than or equal to this infimum. And the more interesting case is to prove the opposite inequality. In here, roughly the idea is as follows. We consider the following function, where f is an arbitrary bounded inner functional on A. And this function is defined in a disk, in the disk of radius 1 over r of A, just by the definition of the spectrum of our element. So the spectrum is the spectrum of A inverse is outside. So this is defined in this disk. And moreover, we can write the Taylor expansion for this function explicitly by restricting this function to the smaller disk of radius 1 over the norm of A. And if we consider this disk, then we can just decompose this function as a geometric progression, and we deduce that its Taylor series looks as follows. But on the other hand, this function is easy to be homomorphic in the bigger disk. So the same expansion holds in the bigger disk. And now by using some simple calculations, we deduce that the spectral radius is greater than or equal to lim sup of the sequence. So it is less than or equal to the infimum, but it's greater than or equal to lim sup. And this readily implies that the limit exists and is equal to infimum, to the infimum. So this is a rough idea of the proof. As a corollary, we get a simple and useful characterization of elements with zero spectrum. The spectrum of A is 0, if and only if the spectral radius is 0. And this happens if and only if this limit is 0. And if you write the definition of this limit explicitly, in terms of epsilon and n, we see that this happens if and only if the sequence of norms of powers of A is rapidly decreasing, in the sense that it decreases faster than any geometric progression for any positive epsilon. For example, if the sequence behaves like something like 1 over n factorial, then this is exactly an example of this situation. And there is a special name for such elements. They are called quasi-nilpotent. Such elements of A are called quasi-nilpotent. The reason for this name is clear. If A is nilpotent, then this sequence is eventually 0. And if it is quasi-nilpotent, it is not necessarily eventually 0, but it is rapidly decreasing in this sense. So this implies why they are called quasi-nilpotent. Probably the most classical example of a nilpotent element, or more exactly of a nilpotent operator, sorry, of a quasi-nilpotent operator, which is not nilpotent, is the so-called Volterra integral operator. Volterra integral operator. So it is defined as follows. We take a bounded measurable function K on square, on the square, AB cross AB, and define an operator V sub K, which acts on the L2 space, L2 of AB, by the following formula. This is the integral from A to X k of xy f of y dy. So this is the so-called Volterra integral operator, and it's a standard exercise in functional analysis to show that this operator is quasi-nilpotent. But not necessarily nilpotent. If k is identically 1, then it is not nilpotent. But it is always quasi-nilpotent. Another useful corollary of the Berlin-Gelfand formula is as follows. If A is one algebra, well, that's to be concrete, let's consider the unital case. Suppose that A is a unital Banach algebra, and B is a unital subalgebra of A, a closed subalgebra, so it is also a Banach algebra, which contains the identity of A. Then the spectral radius for every element B in the smaller algebra B, its spectral radius calculated with respect to A is equal to the spectral radius calculated with respect to B. So these two numbers are the same. Let's recall that the spectra are not necessarily the same. This spectrum is in general smaller than this spectrum, but the supremum is the same. So the spectral radius doesn't depend on the choice of a closed subalgebra. And this is clear from this formula because the formula depends only on the norms, which is the same on B and on A. And so the spectral radius is the same. In fact, this result can be slightly generalized. It's a useful exercise to show that the spectrum with respect to A is roughly, it can be obtained from the spectrum with respect to B by removing some holes in the spectrum. But the unbounded component of the complement of the spectrum will be the same for both the spectra. Okay, so that's all I wanted to tell about the spectral radius. Let's now discuss, or maybe recall, some basics of the theory of commutative Banach algebras. So we now specialize to the commutative case. This theory of the foundations of this theory is also due to Gelfand. And there are two basic notions in the theory of commutative Banach algebra, namely the maximal spectrum and the Gelfand transform. So let's start with the maximal spectrum. First of all, consider commutative algebra A. So first we consider the pure algebraic case, that is, A is not assumed to be equipped with a norm. It's just a commutative algebra. And let's recall the following algebraic definition. If we have a proper ideal, I of A, a proper ideal, we say that A is maximal if it is not contained in any strictly bigger proper ideal. That is, if there is no ideal J such that J is strictly bigger than I and J is a proper ideal. But it's just the maximal element in the collection of all proper ideals. Let me stress that A, we don't assume that A is unital. A is not necessarily unital. If A is not unital, then it's reasonable to consider only those maximal ideals which have the following extra property. We say that an ideal I of A is modular. Some people say regular, but the word regular is a bit overloaded in mathematics. So we say that I is modular if the quotient of A modulo I is unital. So A itself is not necessarily unital, but the quotient is unital. So equivalently, if we write this down explicitly, this means that there is an element, little u, in A, such that for every A minus AU sits in I. So this is an element whose coset modulo I is the identity in the quotient. And this element is called a modular identity. A modular identity for I. So we will be interested in, well, first of all, let's look at some examples of modular and non-modular ideals. First of all, it's clear from the definition that if A is unital, then all ideals are modular. And this happens if and only if the zero ideal is modular. The zero ideal is modular means exactly that A is unital. But if A is unital, then clearly all quotients are also unital, so all ideals of A are modular. On the other hand, it's rather easy to construct non-modular ideals in non-unital algebras. For example, let's look at the algebra with trivial multiplication. Which means that just that the product of any two elements is 0. Then clearly all proper vector subspaces are ideals, and they are not modular. Well, this example is in a sense degenerate, but it's rather easy to construct a more interesting example of a non-modular ideal. Let's, for example, take the algebra of polynomials with a zero constant term. This is non-unital algebra, and let I denote the principal ideal generated by T. That is, in other words, this is it consists of polynomials whose constant term and whose linear term vanish. Then I is a maximal and non-modular ideal. Well, indeed, it is maximal because it has codimension 1. And it is not modular because the product of any two elements in A sits in I. This is clear, and so this implies that the product on the quotient is identically 0. So the quotient is not unital. The product in this is the one-dimensional algebra with a zero multiplication. So we'll be interested in the set of all maximal modular ideals. And the set is called the maximal spectrum. The maximal spectrum of A we'll denote it by max of A. This is the set of all maximal modular ideals of A. By the way, a linguistic remark. In general, there are two possible ways of understanding the combination of words maximal modular. But in fact, an ideal is maximal and modular. Maximal and modular, if and only if it is maximal among modular ideals. And this readily follows from the observation that you will have two ideals, I and j, and I is contained in j, and I is modular, and j is also modular. Well, indeed, a modular identity for I is automatically a modular identity for j, so j is modular. And as a result, if I is the maximal element in the set of all modular, of all proper modular ideals, then it is maximal in the set of all ideals. So this definition is, this definition doesn't lead to any confusion because the two possible ways of understanding maximal modular are actually equivalent. Okay. Here is a useful property of modular ideals. In particular, this property explains why modular ideals are better than arbitrary ideals. We have the following proposition. Every proper ideal of A is contained in a maximal modular ideal. This is a rather standard result. The proof is based on Zorn's lemma. But I'd like to stress, a little warning, that this result fails for non-modular ideals.
But in algebra, in that example with trivial multiplication, we don't have any maximal modular ideals, no?
In which example?
In that example with trivial multiplication.
But, you know, there are no proper, there are no modular ideals at all. So this, well, in this case, the proposition is true because there are no proper ideals. There are no proper modular ideals. Oh, proper modular ideal, of course. I forgot to write this down. Thank you. Of course, proper modular ideal. Every proper modular ideal is contained in the maximum. Here I wrote modular. It is essential that modular is here and modular is here. That is, we consider only modular ideals. Every modular ideal is contained in a proper modular, in a maximal modular ideal. So, if we apply this proposition to this concrete example, then this is just will be stated about an empty set. The set of all proper, or the set of all modular ideals, of all proper modular ideals, is empty. Roughly, the reason why this result fails why the proof fails the standard proof fails for modular ideals is that in a non-unital algebra, the union of a chain of an ordered chain of proper ideals is not necessarily proper. This never happens in a unital algebra, and this never happens for modular ideals. But this can happen for non-modular ideals. And in fact, there are some rather standard counterexamples. For example, well, let me give you such an example. If we take the algebra of the algebra little c0, the algebra of sequences which vanish at infinity, this is clearly an algebra, and actually it's a Banach algebra. And let's consider the ideal of all sequences which are eventually zero. The ideal of finite sequences. Then it can be shown that I is not contained in any maximal ideal. So it's essential that we consider only modular ideals here. Okay. Well, let's look at let's now look at another set, which is closely related to the maximal spectrum. This is the set of all non-zero characters of A. The standard name is the character space. The character space of A is the set, will denoted by A hat, the set of all non-zero characters. It is algebra homomorphisms from A to the complex numbers. A set of all non-zero characters. Well, how is it related to the maximal spectrum? Let's observe that the kernel of a non-zero character is a maximal modular ideal. Is a maximal modular ideal. Well, indeed, it has codimension 1, so it is maximal, and it's modular because the quotient is isomorphic to the complex numbers, so it is unital. So we obtain a map from A hat from the character space to the maximal spectrum, which takes every character to its kernel. It's a rather simple proposition to show that this map is injective. The map which takes every non-zero character to its kernel is injective. There are many important cases where this map is actually bijective. So let's look at some examples. For example, let's consider the case where A is the polynomial algebra in one variable. And in this case, it's a simple exercise to show that our map is bijective. And in fact, both sets, the character space and the maximal spectrum of this algebra, can be identified with the complex plane. Explicitly, if P is a point on the complex plane, then we can take just the evaluation character, as denoted by epsilon P, which takes every polynomial f to f of P. We simply evaluated P. Clearly, this is a character. And this gives us a bijection between the complex plane and the set of all characters. And if we consider the kernel of this character, then such ideals are precisely the maximal spectrum. So this is a set of all maximal ideals of A. Actually, the same result holds for many other algebras. For example, the same is true for the polynomial algebra in several variables. But this is not so elementary. This follows from Hilbert's Neustein-Satz. And moreover, more generally, we can consider the algebra of regular functions on any affine algebraic variety, and the result will be the same. The map between the character space and the maximal spectrum is bijective. But on the other hand, we can also easily construct counterexamples. For example, if we take any field which properly contains complex numbers, well, for example, we can take the field of rational functions in one variable, then the character space is empty. There are no characters. But on the other hand, the maximal spectrum is non-empty. the maximal spectrum consists of the only ideal, that is the zero ideal. So as a result, this map is not bijective in this case. By the way, if we come back to this proposition, we see that if A is unital and non-zero, then the maximal spectrum is non-empty. For every unital non-zero algebra, the maximal spectrum is non-empty. For the simple reason that we can just apply this proposition to the zero ideal, and so it is contained in the maximal ideal, so the maximal spectrum is non-empty. But if A is not unital, then in general this is not the case, and here is a counterexample. In this algebra, in an algebra with trivial multiplication, then we have no modular ideals at all. So the maximal spectrum is empty in this case. Well, if you are unfamiliar with these notions, then I can suggest the following exercise. Try to describe explicitly the character space and the maximal spectrum for the following algebras. For example, for the algebra of polynomials with zero constant term, for the algebra of formal power series, and for the algebra of formal power series with zero constant term. A simple but nice exercise. Okay, so let's now come back to functional analysis, and let's consider commutative Banach algebras. It turns out that for commutative Banach algebras, this map is always bijective, which is a very nice property. More exactly, we have the following result. Suppose that A is a commutative Banach algebra. Then, first of all, every maximal modular ideal. Oh, I'm sorry, before we move to Banach algebras, I'd like to state one more result. One more pure algebraic result, which shows a relation between the maximal spectrum of A and the maximal spectrum of its unitization. It's rather useful because in many situations, to prove some result about non-unital algebras, it is useful to reduce it to unital, to the unital case. So let's introduce some notation. Suppose that A is a commutative algebra. So let's introduce the following set, max plus of A. So this is the union of the maximal spectrum and the algebra A itself. So in some sense, the algebra A is also an ideal in itself, and the quotient is 0. The quotient of A modulo A is 0, which is unital. So A can be considered as a modular ideal in itself, but it is not proper. And another set will be denoted by A hat plus, and it consists of all characters, including 0. All characters of A. In other words, this is the union of the character space and the 0 character. We now have the following result, the proposition. So let's look at the following picture. So let's take the maximal spectrum of the unitization of A. And let's restrict every character of A plus to A. well, the resulting map will be character of A, but not necessarily non-trivial. So as a result, we have a map from this set, from this character space to A hat plus, which takes every character to its restriction to A. By the way, we always have a character, a unital character of A plus, which is identically 0 on A. So that's why we have to put the plus here. On the other hand, we have here the maximal spectrum of A plus, and the character space is embedded in this maximal spectrum. And similarly for A, if we take a set max plus away, then we have an embedding of this set into this set. In both cases, every character goes to its kernel. And finally, we can also consider an arrow from here to here, a map from this set to this set, which acts as follows. It takes every maximal ideal of A plus and takes it to the intersection of I with A. So I claim that, first of all, this arrow is well defined. It exists. The lower horizontal arrow exists. In other words, the intersection of a maximal ideal of A plus with A is a maximal modular ideal of A, or the algebra A itself. There are two options. So this arrow exists, and moreover, both horizontal arrows of this diagram are bijective. And the diagram commutes. The diagram commutes. Well, the fact that the upper horizontal arrow is bijective is clear. This is just a special case of the universal property of the unitization, which was discussed at the previous lecture. But the fact that the lower horizontal arrow exists and that it is bijective is not so obvious, but it's a good algebraic exercise. Okay, let's now move to Banach algebras. For commutative Banach algebras, we have the following important result. Theorem. Suppose that A is a commutative Banach algebra. Then, first of all, every maximal modular ideal, of A is closed in A. And second, the map from A hat to the maximal spectrum, which takes every character to its kernel, is bijective. By the way, let me remark that actually part 1 is a special case of part 2, because we know that all characters are continuous automatically. So the kernel of continuous characters is clearly closed. But in fact, the proof of 2 is based on 1. And that's why I stated both parts of this result. Roughly, the idea is as follows. First of all, to prove part 1, we may assume that A is unital, because if it is not, then we just look at this diagram, and we see that it's suffice to prove this result for A plus, which is unital. So it's enough to consider the case where A is unital, and if we assume that some maximal modular ideal is not closed, then it is dense, for the simple reason that the closure of an ideal is also an ideal. So if it is maximal, then the closure is A itself, so I is dense in A. But on the other hand, a proper ideal is never dense because the set of invertibles is open and is disjoint from any ideal. So there are no dense ideals in a Banach algebra. So this implies that every maximal modular ideal is closed. And if we now consider the quotient of a modulo this ideal, this will be a Banach field, but the Banach field is isomorphic to the complex numbers. And this implies part 2. Okay. So by using this as a result, we'll always identify the character space with the maximal spectrum. This is a standard convention in Banach algebra theory. We'll always identify a hat with the maximal spectrum. By the way, probably it's also useful to observe that in this case, all arrows in this diagram are bijections. So all arrows are bijective. Let's denote it by D, diagram G. So all arrows in D are bijective. Well, because part 2 applies to this part of this diagram and also to this part of the diagram. Okay, this identification between these two sets enables us to topologize the maximal spectrum as follows. We have the following definition. The Gelfand topology on the maximal spectrum of A, which is identified with a hat, and also on the set max plus on the extended maximal spectrum, which is identified with a hat plus, is the restriction of the weak star topology. The restriction to a hat, respectively to a hat plus, of the weak star topology on the dual space, on A star. Which is roughly the topology of pointwise convergence. So the maximal spectrum becomes a topological space. What can we say about the space? So the following result describes some basic properties of the Gelfand topology. First of all, both the maximal spectrum and the extended spectrum max plus of A are Hausdorff. This is clear because the weak star topology is always Hausdorff. Also, the extended spectrum max plus of A is always compact. This follows from the classical Banach-Loglu theorem, which states that the unit ball of the dual space to any normed space is compact for the weak star topology. And so to show that this set is compact, it suffices to observe that this is a closed subset of the unit ball. This is a closed subspace subset of the unit ball, so it is also compact by the Banach-Loglu theorem. As for the maximal spectrum itself, we can always say that it is locally compact. Locally compact. And that max plus of A is the one-point compactification of the maximal spectrum. Well, this is immediate from part 2, because max of A is obtained from the compact set max plus of A by removing a point. So if we remove a point from a compact Hausdorff space, then we get something locally compact, and this will be the one-point compactification of this one. if we come back to diagram D, we can now say that all arrows in this diagram are actually homeomorphisms. All arrows in D are homeomorphisms. And in the special case where A is unital, it turns out that max of A is actually compact, not only locally compact, but is compact. So in other words, this set is compact. So this is the one-point compactification. So we say that this infinite point, this extra point in this set, which is not in the maximal spectrum, is isolated. So both sets are compact. Okay. So these are the basic properties of the Gelfand topology. And let's now introduce the Gelfand transform, which is another fundamental notion of the theory of commutative Banach algebras. The definition is very simple. We define the Gelfand transform of an element or little a in A as follows. This is a function denoted by a hat, the function on the maximal spectrum of A, which is identified with the character space. And it acts as follows. It takes every character chi to chi of A. Looks like something trivial. Well, indeed, the definition is trivial, but it turns out to be very useful. What can we say about this function? It's rather easy to show that it is continuous and vanishes at infinity. The continuity is rather immediate from the general properties of the weak star topology. And it vanishes at infinity because we can define it not only on a hat, but the same formula applies if chi sits in a hat plus in the set of all characters of A. And it vanishes at 0 because 0 is the zero character. So it's a continuous function on the one-point compactification of a hat, and it vanishes at infinity, literally. So it sits in C0. And we can do this procedure for every element in our algebra. And as a result, we get a map from A to the algebra of continuous and vanishing at infinity functions on the spectrum. And this map is called the Gelfand transform of the algebra A. The Gelfand transform of A is the map, well denoted by gamma A. So it takes every element little a to the function a hat. What can you say about this map? Well, we have the following theorem. First of all, gamma is an algebra homomorphism, and its norm is less than or equal to 1. If moreover we assume that A is unital, if A is unital, then gamma is also unital. It takes the identity of weight to the function which is identically 1, and its norm is exactly 1. Well, of course, here we assume that A is non-zero. If A is 0, then of course gamma is also 0. Property 3 relates this map to the spectral radius. For every element A in A, the spectral radius of A is equal to the supremum norm of its Gelfand transform. And if we look at the spectrum itself, this is property 4. Well, let me write it here. Property 4, for every element in A, the spectrum, or more exactly the non-unital spectrum of A, so our algebra is not assumed to be unital, so this is equal to the range of a hat, and we also must add 0 here. And if moreover A is unital, then we have the following formula. The spectrum of A, now the spectrum itself, is exactly the range of the Gelfand transform. Finally, the kernel of the Gelfand transform is equal to the intersection of all maximal modular ideals. Of all maximal modular ideals of A. Or equivalently, it can be described as the set of all quasi-nilpotents in A. So these are the basic properties of the Gelfand transform. Actually, to deal with the Gelfand transform and also to prove this theorem, it's useful to reduce everything to the case of a unital algebra. So let me draw a picture which relates the Gelfand transform of A with the Gelfand transform of A plus. So this is A. This is A plus, the unitization of A. Here we have the Gelfand transform of A plus. It takes A plus to the algebra of continuous functions on the maximal spectrum of A plus. I don't put 0 here because this space is compact, so all functions vanish at infinity. So this is just the algebra of continuous functions. Let's now identify the maximal spectrum of A plus with the space max plus of A, with the extended spectrum of A, by means of this homeomorphism. So we remember that all arrows here are homeomorphisms. So we can identify it with the algebra of continuous functions on max plus of A. But on the other hand, this algebra contains the ideal of functions vanishing at infinity. And since this is precisely the one-point compactification of the maximal spectrum, this is contained in here as a maximal ideal of codimension 1. And here we have the Gelfand transform of A. So if we now look at all these definitions, on the definition of the Gelfand transform, and on the explicit, if we look at the explicit form of identifying these two spaces, which is given in this diagram, we see that this diagram is commutative. So roughly, we see that the Gelfand transform of A is the restriction of the Gelfand transform of A plus. So to work with the Gelfand transform, we can always extend it to unitization and work with the Gelfand transform of A plus. Let's now look at a concrete example of the Gelfand transform. That is, let's consider the algebra of continuous and vanishing at infinity functions on a locally compact Hausdorff space. C0 of X. What can we say about the maximal spectrum and the Gelfand transform? Well, roughly it turns out that the maximal spectrum of the algebra C0 of X is X itself, and the Gelfand transform is the identity map. To state this result more precisely, let's introduce some notation. Suppose that X is a locally compact Hausdorff topological space. And for every point X in X, let epsilon X denote the evaluation character of the algebra C0 of X, which takes every function f to f of X. And the respective maximal ideal will be denoted by mx. So it consists of all functions vanishing at X. So we have the following proposition. Let A denote the algebra C0 of X. Then, first of all, I claim that the map, let's denote it by epsilon, from X to the maximal spectrum of A, which takes every point X to the respective maximal ideal mx, is a homeomorphism. Or equivalently, we can identify the maximal spectrum with the character space. And in this case, epsilon takes every point X to the evaluation character epsilon X. So this is a homeomorphism between X and the maximal spectrum. The key point in this in the proof is the surjectivity. So basically, we have to show that every maximal modular ideal, for every maximal modular ideal, there is a for every proper ideal, not necessarily maximal, for every proper modular ideal, we can always find a point where all functions in this ideal vanish. This is the key point of the proof. And in fact, if you now look at the Gelfand transform of this algebra, it can be identified with the identity map of C0 of X as follows. So I claim that this map is an isometric algebra isomorphism. Isometric isomorphism. And moreover, the inverse map is quite explicit. The inverse map, gamma inverse, so it takes C0 on the maximal spectrum to A, that is to C0 of X. So it is induced by the homeomorphism epsilon. So this map is equal to epsilon dot, which is just the composition with epsilon. It takes every function f to f composed with epsilon. This is just the inverse of the Gelfand transform. So in some sense, this result shows that if we identify X with the maximal spectrum by means of this standard homeomorphism, then the Gelfand transform becomes the identity map. In conclusion, let me say a few words about a useful category theoretic interpretation of the Gelfand transform. Let's consider the following two categories. The first category will be denoted by comp. So its objects are compact Hausdorff topological spaces. So these are the objects, and clearly the morphisms are just continuous maps. And the second category will be denoted by cuba. Its objects are commutative unital Banach algebras. And the morphisms are just continuous unital homomorphisms. So these are our categories, and we have the following two functors, or more exactly contravariant functors, between these categories. The first one will be denoted by C. It acts from comp to cuba. And the second one will be denoted by max, and it acts in the opposite direction. So explicitly, the functors act as follows. If X is a compact Hausdorff topological space, then the functor C takes this space to the algebra C of X of continuous functions. And if F is a continuous map from X to Y, then this functor takes it to the induced homomorphism, as denoted by F dot, similarly to our previous proposition. It acts from C of Y to C of X, and it acts as a composition with F. It takes every continuous function G to G composed with F. So clearly this is a contravariant functor. And the second functor, max, takes every commutative unital Banach algebra to its maximal spectrum, which is compact because the algebras are unital. And if phi is unital algebra homomorphism from A to B, then our map, our functor takes it to the map phi star from the spectrum of B to the spectrum of A. So here it is convenient to interpret points of the spectrum as characters. And it takes every character chi to chi composed with phi. So basically, this is just the restriction of the dual map between the dual spaces, restriction of the dual map to B hat. It is continuous because the dual map is always continuous for the weak star topology. So what if we compose these functors? So there are two options. We can first apply C and then max, or we can apply first max and then C. So the answer about these compositions is given in the following simple proposition. If we look at all homomorphisms of this form, consider such homomorphisms for all compact Hausdorff topological spaces, then we get a natural isomorphism. A natural isomorphism between the identity functor on compact spaces and the composition of max and C. So the composition of these two functors is isomorphic to the identity functor. What if we compose our functors in the opposite way? First max and then C. In general, this is not isomorphic to the identity functor, but it is related to the identity functor by means of the Gelfand transform. More exactly, the Gelfand transform, if we consider the Gelfand transform for all commutative unital Banach algebras, then we get a natural transformation, that is a functor, a morphism of functors, from the identity functor on cuba to the composition of C and max. And moreover, I claim that we have the following natural bijection. We have a natural bijection between the set of all morphisms of commutative unital Banach algebra from A to C of max of A, and the set of all continuous maps, that is morphisms in the category of compact spaces, from X to max of C of X. And this bijection is quite explicit. Indeed, if we have, say, a homomorphism phi from here to here, then the corresponding map from x to max of C of x is constructed as follows. First, we apply epsilon x, which acts from x. Of course, not C of sorry. Of course, this should depend on A, maximal spectrum of A. So epsilon x acts from x to the maximal spectrum of C of x. And if we compose it with the induced map phi star, we get a map from A to C of max. So we have many.
I think it should be
C of x, of course. Thank you. C of x. Well, epsilon x acts from x to max of C of x. Yes, and phi star takes max of C of x to max of A. Good. Now it is, I hope it is correct. And conversely, if f is a map from x to max of A, we can do the following. We first can apply the Gelfand transform of A. It takes A to C of max of A. And if we compose it with f dot, we will be in C of x. And so these maps are inverses of each other. To make this bijection more useful, it's reasonable to consider the dual category, the category dual to comp. So we simply formally reverse all arrows. And so we have morphisms in this category from max of A to X. So in other words, if we look at this bijection, we see that the functors max and C form an adjoint pair. This is an adjoint pair of functors. So this is a category theoretic interpretation of the Gelfand transform. Okay, so that's all for today. At the next lecture, we begin considering C-star algebras. We discuss again without proof some basic results about them, including the first Gelfand-Dirac theorem, which tells us that if we reduce this picture to commutative unital C-star algebras, then we get an equivalence, an anti-equivalence of categories between commutative unital C-star algebras and compact Hausdorff topological spaces. And then we'll discuss some constructions which lead to another fundamental result, namely the second Gelfand-Dirac theorem, which tells us that any, not necessarily commutative, an arbitrary C-star algebra can be embedded into the algebra of bounded linear operators on the Hilbert space. So actually it is isomorphic to a closed star subalgebra, to a closed self-adjoint subalgebra of the algebra of bounded operators on a suitable Hilbert space. Okay, thank you.